Hello and welcome to today's lecture on dynamic power dissipation. We have started our discussion on various sources of power dissipation in Cmos circuits in the last lecture, and I have mentioned about two different types of power dissipations. Rather, you can categorize the sources of power dissipation into two types, dynamic and static. And in the last lecture, I have introduced the switching power dissipation, which is one of the components of dynamic power dissipation. And today we shall continue our discussion on switching power dissipation, and then as we shall see later on, I shall discuss about the short circuit power dissipation, which is another component of dynamic power dissipation. So, here is the agenda of today's lecture. Essentially, I shall briefly recapitulate about the types of power dissipation, then classification of sources of power dissipation. As I mentioned, we are focusing on dynamic power in this lecture. I have already started discussion on switching power dissipation, and it will be followed by short circuit power dissipation and glitching power dissipation. And later on, I shall discuss about the degrees of freedom. That means, what are the parameters you can use to reduce dynamic power dissipation, rather what is your handle in reducing the power dissipation. We have discussed about three types of power in my last lecture: peak power, average power, and this difference between power and energy. As you know, peak power is very important because at any instant of time, what is the maximum power that is being that is drawn by the circuit in operation is very important for reliable operation of the circuit. And as you know, because of the peak power, there is transients on the power lines, and that may lead to glitch and error in the signal. We are not going to discuss in detail today. Similarly, the average power is important, particularly for battery operated embedded systems, battery operated portable systems, where the life of the system depends on the battery, on how long the battery can sustain the power, and on the average how much power dissipation is taking place, that is very important. That is why most of our discussion will be based on this average power dissipation. And I have mentioned about the difference between power and energy. As we shall see, actually in case of your battery operated systems, energy is the most important thing, and so sometimes we use power and energy I mean without making any distinction, but that is not true. Actually, energy is the energy is very important in battery operated systems, and essentially we are talking about reducing energy that is being drawn by the portable system whenever we are discussing about low power systems. Now, as I mentioned, we discussed about classification of sources of power dissipation, dynamic power, and the most important component of this dynamic power is the switching power. And in the last lecture, we have derived the expression for the switching power dissipation, and which is equal to alpha L, where alpha L is the load, capacitive load, alpha L is the switching activity, Cl is the load capacitance, VDD is the supply voltage, and F is the frequency of operation. So, this is the power dissipation that occurs because of the charging and discharging of the load capacitance, and so it is equal to alpha L Cl VD square into F. And as you have seen, there are many internal loads where also power dissipation occurs, and that can be represented by alpha I dot Ci dot VDD into VDD minus Vt, I mean summation of all such different nodes. And you may note that here instead of VDD square, there is a term VDD into VDD minus Vt. The reason for that is, for internal loads, the power the supply voltage does not change between 0 to RL. I mean VDD. Actually, when you charge a internal load, it can reach up to VDD minus VT, and as a consequence the equation is little different from the power dissipation of the output capacitive load. Okay. So, with this background, now we shall focus on transition probability in dynamic circuits. We have already discussed about the switching activity of static Cmos circuits, and we have seen that the switching activity can be represented by P 0 to 1, which is equal to P 0, which is where P 0 is the probability of remaining the circuit in with output 0, and P 1 is the probability for remaining the circuit in 1. So, from this you can find out the switching activity in static Cmos circuits, and we have discussed in detail how this can be calculated in different situations and for different types of gates, NAND, NOR, exclusive OR and so on. And also you have discussed about how the switching activity changes as you change the fan-in. Now, what about dynamic Cmos circuits? In case of dynamic Cmos circuits, we know that the output is precharged to always output is precharged to VDD. It is always precharged to VDD. Then of course, during the evaluation phase, it may discharge to 0 or remain VDD, output remain VDD. That means the output may make a transition from VDD to 0 or it may remain at VDD. So, this is how the dynamic Cmos circuit works. But in such a situation, as you can see, always in each, I mean for each computation, you have to charge the output to VDD. That means, what we can say that P 1 probability that the output will be 1 is always 1, and as a consequence if you substitute in this, then P 0 to 1, the switching activity will be equal to P 0. That means, since we are always charging to 1, either it may make transition to 0 or may not make transition. That is why the switching activity is equal to the probability of transition to 0, not the P 0 into P 1. So, obviously, this switching activity will be more in dynamic Cmos circuits, because always you are precharging the output to 1, and it may either discharge or may not discharge, and as a consequence the switching activity is more. As you can see for different types of gates, what is the switching activity, transition activity. For inverter it is 1 by 4, and you may recall that for static Cmos circuit it was 1 by 4, not half, but 1 by 4. It was because P 0 was P 0 is half for inverter, because output may become 0 or 1, and as a consequence the probability of becoming 0 is half, probability of becoming 0 is also half, and as a consequence P 0 to 1, that is switching activity, was 1 by 4. But in this particular case for inverter it is equal to half, not 1 by 4. Similarly, for 2 input NOR gate it is equal to 3 by 4, and because as you know, in case of NOR gate probability of becoming the output 0 is 3 by 4, because it will become for whenever for NOR gate, whenever both the inputs are 0, output is 1, and so whenever any one of the inputs are 0, I mean 1, then output is 0, and as a consequence the for 2 input NOR gate it is 3 by 4, and 2 input NAND gate it is 1 by 4. And in case of static Cmos circuits, you may recall that this was equal to 3 by 4 into 1 by 4. So, 3 by 16, and for 2 input NAND gate it was also 3 by 16. That means, if we compare, we find that say for inverter, say for static Cmos, and say dynamic Cmos, if we compare, for inverter it is 1 by 4, for dynamic Cmos it is 1 by 2, for 2 input NOR, not 2, it is here it is 3 by 16, here it is equal to 3 by 4. For NAND 2 and 2 it is 3 by 16, but here it is equal to 1 by 4. So, we find that the for dynamic power dynamic CMOS circuits, the switching activity is more. But you may recall that I mentioned that in dynamic CMOS circuits the overall power dissipation is less. Why so? The reason for that is although the switching activity is more, but the overall capacitance is much less, and overall capacitance is less, and secondly you will see that the output is driving to one of the capacitors, I mean one of the transistors, not both, I mean either either NMOS or PMOS. As a result, the load capacitance is also less. That is the reason why, although switching activity is more, but the power dissipation is usually lesser in dynamic CMOS circuits. Okay. Now, another very important aspects of dynamic CMOS circuits is power dissipation due to charge sharing. In case of dynamic gates, power dissipation takes place due to phenomenon of charge sharing even when the output is not 0 at the time of evaluation. As we know, in static CMOS circuits, power dissipation, dynamic power dissipation occurs only when output changes from 0 to 1 and 1 to 0. If the output remains 0 in consecutive computation, there will be no dynamic power dissipation in dynamic CMOS circuits. But unfortunately, that is not true in case of dynamic CMOS circuits. So, in case of static CMOS circuits, you will find that dynamic power dissipation occurs only when there is a transition at the output. But even when there is no transition at the output in dynamic CMOS circuits, then there can be dynamic power dissipation because of charge sharing. How? Let me explain here. So, this is a dynamic CMOS gate. Essentially, it is a 3 input NAND gate, and as you can see, in addition to the output load capacitance, there are three nodes. 3 nodes, one node is here, another node is here, another node is here. The third node, there is also a capacitance here C3, which is not mentioned. So, let us assume that initially our input was 111. So, whenever the input is 111, then as you know, the output will be 0. So, all these capacitors will be discharged. Now, suppose input is 110. So, whenever you make it 110, output will switch to 1. So, at that time this capacitor will charge to VDD during the pre-charge phase. So, what will happen? Let me redraw it to explain the operation. So, here you have got a PMOS transistor, then there are 3 NMOS transistors, because it is a then of course, there is a another transistor here which is connected to clock. So, this is connected to clock because it is a dynamic CMOS circuit. It is connected to VDD, and these are the 3 inputs A, B and C. So, you have got one load capacitance here CL, and here a load capacitance C1, then another capacitance C2 and another capacitance C3, 3 capacitance. So, initially you have applied the input 111. So, 11 means this V out is 0, V out 11 means V out is equal to 0. Now, the second input, that means at that time, since this transistor is on, let me give the name Q1, Q2 and Q3, all are on, then what will happen, all these capacitors will be discharged, not only CL, but C1, C2 and C3 all will be discharged. Now, suppose the next input is 110, that time the output is precharged during the precharge phase, output is precharged to VDD. Now, What will happen during evaluation phase? This is during pre-charge. So, during evaluation phase, what will happen, this capacitor here the charge is CL into the charge that has been accumulated is CL into VDD. So, this is 0, this is 1, this is 1. So, A, B, C. So, what will happen, this transistor is off, Q3 is off, but Q1 and Q2 these two are on, and as a consequence since this transistor is on, this transistor is on, this charge will get redistributed in C1 and C2, and since earlier input was 111, these two capacitors were discharged, what will happen, this charge will get distributed in C1 and C2, and as a consequence what will happen, the output will become will because of redistribution the output will be not VDD, say it will attain a new value V nu, let us assume, because of redistribution of charge. So, how do you calculate V nu? You can calculate it in the same way, because by considering the conservation of charge, say C1 plus C2, C1 plus C2 into plus CL into V nu, this is the new total charge, I mean this is the total charge, that will be equal to CL into VDD. So, V nu will be equal to CL by C1 plus C2 plus CL into VDD. Of course, here I have not taken into consideration that this capacitor will not charge to VDD, but it will charge to VDD minus VTD. That of course you can take into consideration. That means this will be here you will be having actually C2 into V nu minus, here it will be C2 VT plus C1 VT, these two factors will be there. So, this you can take into consideration while computing, but the main point is output will not be equal to VDD, but less than VDD, it will reduce, because this factor will be more than CL, and as a consequence it will drop. Now, next time whenever you apply the same input, what will happen? Again from V nu it will charge to VDD. So, next time you are applying the same input. So, in case of static CMOS circuit there will be no change in the output, but in case of dynamic CMOS circuit it will charge, output will charge from V nu to VDD during pre-charge phase, and again during evaluation phase it will be get discharged to a new level, that is your V nu. So, and as a consequence there will be a dynamic power dissipation, and here you can see that delta V, which is the change in the voltage, is equal to VDD minus CL by C1 plus C2 into C3 into VDD, and that leads to that makes a difference, and as a consequence this is the power dissipation that will occur, because in spite of the fact that you have applied the same input, there will be some power dissipation at the output, that is equal to CL into VDD into delta V, that is CL into C1 plus C2 by C1 plus C2 plus CL into VDD square. So, this is a new component that is only present in dynamic CMOS circuits. That means, power dissipation due to charge sharing can occur only in dynamic CMOS circuits. It does not occur in static CMOS circuit. Okay. Now, having discussed the switching power dissipation in static CMOS and dynamic CMOS circuits, now let us take up an example. Here is an example where we have got where we have to realize a function, that function is equal to, let us assume function that you are realizing is equal to f is equal to, it is a OR function, say A or B or C or D or E or F. So, it is a 6 input OR function you are realizing. Now, you can realize this function in a number of ways. So, first technique can be, you will use a 6 input NOR gate, 1, 2, 3, 4, 5, 6. So, A, then you will apply B, C, D, E and F, 6 inputs, then you will put an inverter to realize the OR function. So, this is the first technique of realizing your 6 input OR function. Second alternative is, what you can do in the first stage, you will have two NOR gates, A, B, C you apply here, A, B, C and D, E, F, D, E and F is applied here. Then you will require a 2 input NAND gate instead of inverter at the output stage to realize the function f. In all the cases, the function realized is f. And third alternative that you can have is, you can have 3 2 input NOR gates in the first stage. So, A, B, then C, D, then E and F. So, and then you will require a 3 input NAND gate. So, in all the 3 cases you are realizing the same function. So, at the time of what is known as technology mapping, you can choose one of the 3 configuration in realizing the function. Normally, in the standard cell library, you will get inverter, you will get 2 input NAND and NOR gates, you will get 3 input NAND and NOR gates. So, you can and also you can have 4 input NAND and NOR gates and up to 6 input NAND and NOR gates. So, whenever you do the realization in one of the 3 ways, is there any difference in area, power dissipation? Because our main concern is power dissipation, but you have to also look into other 2 parameters, which is power and performance. So, let us try to compare the differences in area, performance, speed of operation and the dynamic power, rather switching power, that we shall compare for these 3 circuits, and let us assume we are realizing using static Cmos circuits. So, now let us consider, to compute the dynamic power, you have to find out the switching activity. So, what will be the switching activity at this point, at this point, at this point. So, here let me give the name of this node as output 1, O1. Here it is, there are 2 outputs, O1 and O2. Here 3 O1, O2 and O3 internal nodes, and finally you have got the final outputs. Now, what is the switching activity at internal node O1 in the first case? As you know, it is a 6 input NOR gate, and as you know, the switching activity will be equal to 63 by 4096. The reason for that is, it will be 1 by 2 to the power 6 into it will be 63 by 2 to the power 6. So, that gives you 63 by 4096. So, that will be the switching activity here, and same switching activity will be taking place here as well, because the number of transitions that will occur at this point will be same as the number of transitions that will occur at this point, because this is a simple inverter. So, this is the switching activity. Now, what will be the switching activity at this point? At this point, the switching activity will be equal to 7 by 64, that we are getting because it is a 3 input NOR gate. So, the switching activity is equal to 1 by 2 to the power 3, that is your 16 2 to the power 3 is 8 into 7 by 8, that makes it 7 by 64. So, same will be the switching activity at this point. However, at this output the switching activity will be the same, 63 by 4096, because these 3 inputs are considered to be independent, assuming that A, B, C, D, E, F all are independent and they have equal probability of becoming 1 and 0, you will get these switching activities. What about this particular case? In this particular case, the switching activity at this point will be equal to only 3 by 16, that we are getting from 1 by 4 into 3 by 4, and the same will be for all the three inputs, all the 3 points. In all the 3 points, the switching activity will be 3 by 16. However, switching activity here will be 63 by 4096. So, from this we observe that the switching activity of this particular implementation is much less at this point, 63 by 4096. On the other hand, switching activity is more at this point and at this point, that is 7 by 64, and here it is still more 3 by 16 at 3 points. So, from this simple observation we may tell that the switching activity for implementation 3 will be much more compared to implementation 1. Now, let us have a comparison of this. So, here I have taken from some standard cell library specification. You can see the in area for different cells, inverter, NAND 2, NAND 3, NAND 6, NOT 2, NAND 3 are given here. Relative area. So, cell unit is 2 for inverter, cell unit is 3 for NAND gate, for NAND 3 gate, the 3 input NAND gate it is 4, 6 input NAND gate it is 7, for 2 input NOR gate it is 3, and to 3 input NOR gate it is 2. So, an input capacitance, as you know, is dependent on the fan in. So, for inverter the input capacitance is 85 femtofarad, and for 2 input NAND gate is 105 femtofarad, for 3 input NAND gate is 132 femtofarad, for 6 input NAND gate is 200 femtofarad, and for NOR gate you can see it will be very close to 2 input NAND gate. So, it is 101 femtofarad. The input capacitance. For 3 input NOR gate the capacitance is 117, and output capacitance, however, it will be same 48 nanofemtofarad for all of them. Of course, here we have not, this is the intrinsic output capacitance. You may have some output capacitance because whenever you are driving a capacitive load or you are driving some other gates, then of course, the load capacitance will be more, and which is expressed by this expression. The average delay will be dependent on the output capacitance. So, for inverter it is 0.22 plus 1 into C0, for 2 input NAND gate it is 0.3 plus 1.24 C0. You can see this factor is increasing because of increasing fanning, and for 3 input NAND gate it is 0.37 plus 1.55 C0 into C0. For 6 input NAND gate it is 0.65 plus 2.30 into C0, and 2 input NOR gate it is 0.27 plus 1.5 into C0. So, these are the average delays in nanosecond, and for 3 input NOR gate it is 0.31 plus 2.0 into C0. So, based on these parameters you can calculate the dynamic power dissipation. So, of course, we are not interested in absolute values, but we can calculate the relative values which are shown here. The switching activities I have already mentioned for the 3 nodes. This is for implementation 1, the switching activities are given here at and for implementation 2 the switching activities are given here, this P0 and P1 both are given, and for implementation 3 the switching activities are also given here. So, the switching activity for different nodes I have already mentioned, these are the different values of switching activities. So, using these switching activities you can calculate the dynamic power dissipation, and also you can calculate area, and you can calculate delay from this. So, here is the comparison. For implementation 1, area is equal to 9 because you are requiring one 6 input NAND gate and followed by an inverter. So, 6 input NOR gate and inverter, actually here it will be a NOR gate, I have made my mistake, I have written NAND anyway. So, it will be 9, area is 9, delay is 1.1, you can calculate delay for both the gates and using these equations, and you will get 1.1 nanosecond, and the power dissipation is equal to 6.7. 6.7 power dissipation is actually switching activity into load capacitance. That has been calculated, and this is the sum of the switching activity and load capacitances 6.7 in this case, and so the power dissipation cost is 442.5 in the second implementation, and delay is 0.85, and area requirement is 11 because you are requiring 3 3 input NOR gate followed by 2 input NAND gate. So, 3 plus 4 into 2, that is 8 plus 3 11, that is given here. And similarly, for the third case you will require 3 2 input NOR gate, 3 into 3 9 plus 1 3 input NOR gate, 9 plus 4 13 unit area, and delay is 0.87 and power dissipation cost is 82.4 for the third implementation. So, from this it is evident that although the implementation 1 is area efficient, but delay is more and power dissipation is less. That means, implementation 1, for implementation 1 dynamic power dissipation is less, area required is less, but delay is more. For implementation 2, we find that area is more than implementation 1, delay is less, but the power dissipation is much higher. For implementation 3, power dissipation is much larger because of higher switching activity at the 3 nodes. We have seen that the switching activity is much more here for 3 by 6, 3 by 16, 3 by 16, 3 by 16 and 3 by 16 at 3 nodes. So, these are the 3 nodes here, here and here. and as a consequence, whenever you go for low power implementation, obviously the implementation 1 is more suitable, but whenever you go for minimum minimum delay, then of course implementation 2 or implementation 3 is important. So, this particular example clearly demonstrates that you may realize the same function in different ways by choosing different cells from the cell library, and that may give you different area, different delay and different dynamic power dissipation. So, depending on your requirement, you can choose, you can do the technology mapping. Okay. So, with this example, now we shall come to another important types of power dissipation. We are switching gear to a new types of circuits, that is short circuit power dissipation. And as you already know, short circuit power dissipation occurs because of slow change in the input, and particularly as the input is rising, changing slowly, either going from 0 to VDD or from VDD to 0. In the middle portion, when the input is above more than the threshold voltage of the NMOS transistor, and also when it is VDD minus VTP, in this part there is a short circuit between the supply voltage and ground. I have already mentioned about it, and then there is power dissipation, and that power dissipation we shall compute now, and this is known as short circuit power dissipation. So, here we have taken an example of an inverter. Although an inverter example has been taken, it is applicable to any CMOS circuit. Only difference will be, instead of the PMOS transistor as pull up, you will have a network of PMOS transistors in the pull up and a network of NMOS transistor as pull down, but otherwise the derivation will be very similar. Now, let us consider how the power dissipation is occurring. Let me redraw it. So, here you have got an inverter, static CMOS inverter. This is a PMOS transistor, this is a NMOS transistor pull down, and this is VDD and this is ground. Okay. So, you are applying V in, you are getting V out. Now, say whenever you are changing the inputs, let us assume your input is like this. This is your input So, output will have uh, opposite phase. This is the output. So, this is V in, this is V out. Now, here you have got 3 points, here also 3 points. This is time t1 when this is time, I mean this is the time t1 when the input is reaching Vtn, that means input is going from 0 to Vtn, this is T1. Then the power dissipation is starting, I mean the short circuit is getting established, and it will continue until your this is your this point is Vtn here, and this is the point corresponding to Vdd minus Vtp, absolute value of Vtp. And in between of course you will be having Vdd by 2 point. Here also you will have 3 points, T1, T2 and T3, and here say let us assume T4, middle point is T5 and end point is T6. So, during this period conduction is occurring and power dissipation will occur. So, if you draw the current, this is your IDS. So, you will find that it will be somewhat like this. We have already discussed about these characteristics. So, it will start at T1, continue up to T3, and again it will start with at T4 it will continue up to T6. So, we shall derive expression for this current. How can you derive? So, first let us calculate the current. What is the mean current that will flow? Obviously, as you can see, this current is not small, is not constant. It will attain a peak value when the input is equal to Vdd by 2. Both the transistors are in saturation, maximum current will flow. Then it will, it will again it will fall. So, current is not constant. So, what is the average current that will flow? So, this is equal to 2 into 1 by T. 1 by T is the period. Period means in one cycle. In one cycle you will be having one low to high and another high to low transition. So, accordingly here you will have high to low and low to high transition. So, since they are symmetric, let us assume that both of them are symmetric, that means these two transistors are their switching characteristics are identical. Assuming that, we may write 2 into 1 by T, and you can take summation from T1 to T2 IT into dt plus T2 to T3 IT into dt. So, this is only for the first transition. Since for the second transition it will be same, we have just multiplied by 2 and then taken the average over a period of 1 by T. Now, what is I mean? Again these two can be assumed to be same. So, what we can say that this part, if it is symmetrical, that means if we divide it into two parts, T1 to T2 and T2 to T3, again you can simplify it, say it will be 4 by T and only T1 to T2 IT dt, assuming that all the transitions are symmetric in the sense that they for each of them the one may be mirror image of the other. For example, in this particular case this is mirror image of the other one, but the current, that area for both the curves will be identical. So, we can calculate this. Now, in this particular case what will be the I mean that we can calculate? This is equal to 4 by T T1 to T2. What is IT? Assuming that the transistor is in saturation, because we know that it is occurring when the input is above the threshold voltage of the NMOS transistor. and it is going up to VDD by 2. So, during this period the transistor will be in saturation. So, as you know the expression for current is beta by 2 into VDD minus VTN square. So, we can write beta by 2 into V in T, input is changing, minus Vt whole square into dt. Now, what we can do? We can make the substitution V in T is equal to VDD by tau into T. So, here what we have made one simplification, we are assuming that the input is rising linearly, So, input is rising linearly. So, as a consequence your V in T is equal to VDD by tau, tau is the rise time, and at an instant it will be, the voltage will be equal to VDD by tau into Vt. So, in time tau it will reach VDD. So, at any instant of time t it will be equal to VDD by tau into t. So, we can substitute this here and this will become equal to, and okay, you can make some more substitutions. So, here T, what will be the value of T1? If we substitute T1, then it will be equal to tau by VDD into Vt. As we know, when the input is equal to Vt, then the time is T1. So, it is tau by VDD into Vt. Similarly, for T2 it will be equal to VDD by 2. So, T2 will be equal to tau by 2, because VDD will become VDD by Vt by Vt will be equal to VDD by 2. So, VDD will cancel, it will be equal to tau by 2. So, this we can substitute in this expression. So, after substitution what we shall get is I min is equal to 2 beta by 2, then it is will be equal to T by VDD into Vt, and here it will be tau by 2. So, we have substituted in place of T1 tau by VDD into Vt, and for T2 tau by 2, and here it will be equal to VDD by tau into T minus Vt into dt. Of course, here there will be a square. Now, again we substitute VDD by tau into T is equal to minus Vt is equal to x. Then VDD by tau into dt, if we differentiate, that will be equal to dx. So, this if we substitute here, what we shall get? Here by substituting this, it will become I min is equal to 2 beta by t, so this is t into, sorry, it was 2 only. So, that has come from this expression 2 beta by tau, that average value will be, earlier it was, okay, sorry, it will be t only, t. So, 2 beta by t into here it will go from 0 to VDD minus by 2 minus Vt x square. So, this is x we have substituted, and this is dx into, of course, this factor will be there, tau by VDD. So, then this will be equal to 2 beta by t into tau by VDD into x square x cube by 3 by after integration. So, if we substitute x, what we shall get? After substituting x, we shall get, this is I min will be equal to 2 beta by T into tau by 24 VDD into VDD minus 2 VT whole cube, or you can simplify is beta by 12 VDD into VDD, we can rewrite it 2 VT whole cube into tau by T. Now, this is the current. So, the power dissipation will be equal to P short circuit will be equal to VDD into that will be equal to beta by 12 into this VDD will cancel with this VDD. So, we shall get VDD minus 2 VT cube into tau by T, or this T can be written as F anyway. So, this is the expression. So, this we can write into F instead of tau. So, what does this expression tell us? This expression tells us that the short circuit power dissipation is proportional to the frequency of operation F. It is proportional to the rise and fall time, that is the transition time. It is proportional to VD minus 2 VT cube. It is dependent on the supply voltage, and also it is dependent on beta. You know, in beta we have the parameter that is mobility of electron, then we have the parameter width of the transistor, length of the transistors. So, the short circuit power dissipation is dependent on the physical dimension of the transistors, mobility of electrons and holes, the transition time, rise and fall time of the input, and the frequency of operation, and of course, last but not the least component is the supply voltage, because there is a factor of VDD minus VT 2 VT and cube. So, this is the short circuit power dissipation expression, and obviously this expression, this particular current is significant in some circuits when the input is changing slowly. Now, as the supply voltage is reduced, what impact it has got on this short circuit power dissipation? So, here I have explained the transfer characteristic for different supply voltages. As you can see, as the supply voltage is reduced from 5 volt to 4 volt, assuming Vtn is equal to 1 volt and Vtb is equal to minus 1 volt, we can see the characteristic curves will change, and the region of short circuit power dissipation is also getting changed. And when we are reaching the point VDD is equal to Vtn plus absolute value of Vtp, at that point what will happen? At that point, as we know, the transfer characteristic will be somewhat like this, and this is the point where you have got Vtn, and also this is equal to absolute value of Vtp. This is the point, and of course, this is VDD. So, at this point we find there is no slow transition. That means, this is VDD and here it is VDD, and when the transition is occurring in the middle, it is changing abruptly and there is no current flow through the circuit, because as at that point initially the NMOS transistor is on, this is PMOS transistor is on, and here NMOS on. So, there is no point where both the transistor is on, and as a consequence what will happen, there is no short circuit power dissipation. So, you may say that why not use a supply voltage which is equal to Vtn plus Vtp, absolute value of Vtp. But unfortunately, if you do that, then you will see that delay will increase, delay will be very high. So, although this is a way of reducing the short circuit power dissipation, but this technique cannot be used because of high delay of the circuit. And another situation is when the input voltage is less than this, that means if the input voltage is whenever VDD is less than VTN plus VTP, will the circuit operate in this particular case? Yes, the circuit will operate, but the transfer characteristic will have a kind of hysteresis. As you can see, when the input is increasing, it is going from, say, initially the output is VDD, then at this point the PMOS transistor is turning off, and during this period, since the output is already charged to VDD, it continues until this point when the NMOS transistor is turning on and output is brought down to 0, and then it is going to VDD. On the other hand, when it is when it is reduced from VDD to input is reduced from VDD to 0, you can see it will follow this path. So, the initially the NMOS transistor will remain on, and it will remain on up to this point, and then it will continue, the output will remain continue to be 0, because output none of the transistors are on during this period, and at this point where VDD minus VTP, absolute value of VTP, again it will rise to VDD, because the PMOS transistor will turn on. So, we find that during this period none of the transistors are on. So, between this VDD minus VTP to VTN. So, during this part of the curve none of the transistors are on, and you will get a kind of hysteresis. If you draw the transfer characteristics, you will get a hysteresis. So, circuit will operate, but you will find that delay will be very high. The reason for that is, you can see while in the input is increasing, only for this part PMOS transistor is on, and during this part none of the transistor is on. Similarly, while when the input is reduced from VDD to 0, during this period the NMOS transistor is on up to this point, and during this period none of the transistors are on, and then again PMOS transistor is turning on to bring it to 1. So, delay will be very large. Okay. Now, how the short circuit power dissipation changes as you change the rise and fall, the transition time of the input, that means the value of tau. We have seen that there is a dependence, linear dependence on the value of tau. So, here you can see. So, how the short circuit power dissipation will change? You can see we have plotted for 3 different values of tau, 1 nanosecond, 2 nanosecond and 5 nanoseconds. Obviously, when the rise time and fall time is equal to 5 nanosecond, that time we find that this area is much larger. That means, this particular area that will be covered by this triangle will be much higher than when it is tau is equal to 1 nanosecond. So, this is the current that will flow for different rise and fall time of the input signal. So, this shows how the power dissipation will change as you change the rise and fall time, and that is the reason why we insert buffers at regular interval in a circuit, so that the rise and fall times are not very high. They should be kept within certain limit. Coming to a third important aspect, you can see we have short circuit power dissipation for different load capacitance. So, initially the load capacitance is 0, and then we have increased the load capacitance, and you can see the curve is going down, because it will not charge to a higher level, but it will go down, and as a consequence the current that will flow will be smaller, and the area that will be closed by this rectangle, by this triangle, will be less. That means, when the load capacitance is increased, the short circuit power dissipation gets reduced. However, although the short circuit power dissipation reduces, the delay will increase because of increased capacitance. So, from this discussion, what conclusion we can make? So far as the short circuit power dissipation is concerned, we have seen there are 3 important parameters. which you can control. One is frequency of operations, but we cannot usually compromise on performance. That is the reason why we cannot really reduce frequency to reduce short circuit power dissipation. However, we can reduce tau. We can also reduce the parameter, that is your sometimes we can reduce the load capacitance, and load capacitance can be increased to reduce the short circuit power dissipation. And of course, the supply voltage scaling or reduction of the supply voltage is the most important parameter, important parameter that can be used to reduce the short circuit power dissipation. So, with this we have come to the end of today's lecture. In the next lecture, we shall primarily discuss about the leakage power dissipation, but before that we shall also discuss about the dynamic power dissipation due to glitching. There is another power dissipation that is known as glitching power dissipation, that we shall discuss in the next lecture. Thank you.